Thanks, Alec, for keeping the time, as I also have to rush out just after this presentation, but it's great to be back in Lisbon. So this is joint work that I present together with colleagues from University of Neuchâtel and from an industry partner, in this case, Edelweiss Connect, that builds platforms for the life sciences. So you may wonder, I maybe help you parsing the title, what is the LLM-assisted interpretation of graphene image analysis in a serverless workflow? So we are talking about material science in general. If I get it to...
Minimize it. Left button. Now you can try it if you want.
No, but I cannot switch the slides. How do I switch the slide?
You're in Zoom. Sorry. You're seeing your screen in Zoom.
Okay, perfect. That's much better. So we do have a trend, which is new materials. In material science, we find super materials such as graphene that are affecting a lot of new products, such as clothing or household devices, which is popular for many reasons, but it's also quite dangerous if applied incorrectly to the human health, to the environment. There's different versions of graphite, graphene oxide. I won't go into the chemical details, but what is quite important is that we analyze such material before it comes to the market, before it is used in the product. And so there are big European platforms being created, such as Accord, where a lot of stakeholders from the industry, manufacturers, government agencies, regulators, chemical experts, material experts, they're all coming together. What's missing is kind of the computer scientists who can help to digitalize the processes, because traditionally the analysis of materials has been done in a lab facility with chemical analysis, or even with animals, lab rats, or human patients in experiments. So in order to digitalize it, we need huge knowledge infrastructures where all the data, all the models are stored. And we use different workflows to capture new materials through certain information, such as images. So in this talk, I will focus on the image analysis, which is not sufficient. You still need to complement it, maybe with chemical analysis. And here you see such an example. So this is a result from the ongoing work where a domain expert, let's say a data scientist with background knowledge in material science, can take a microscopy picture, which is the one you see on the left side, augment it with some pre-processing, which is what you see on the right side, with lots of parameters. We are talking about very complex problems, hundreds, if not thousands of parameters, which can apply depending on the source, the magnification level, the zoom level, the properties of the material, and so forth. And so all of that leads to a lot of output metrics, which then require interpretation by experts. So if you just get a number of metrics and you feed this into the government, because the government asks you to create a report before you can bring a product to the market, they won't understand all of those numbers. So we started investigating LLM-based material analysis interpretation. That means all of the numbers are taken. We are creating reports, human readable reports, with executive summaries, with highlighting of the biggest risks. We are, first of all, starting with the material characteristics analysis, then going to the hazard detection. Is it hazardous for humans? Is it hazardous for the environment? And then finally ending up with a risk assessment, which is also taking the exposure levels into account. So if you are exposed to a little bit of loose graphene, it probably doesn't matter so much if you inhale 1 or 2 liters of it, you may die. So that's also why the governments, especially in Europe, are quite concerned with accelerating the development of such platforms to make sure that our future products are safe. In addition to human-readable reports, we also generate the product passports. You may know that in Europe now there's an obligation to have a digital product passport that informs about all the sourcing of your materials. Has it been tested in the lab? Has it been tested in simulation? What are the health characteristics? And so these platforms can also generate digital product passports. So this was the story behind it, the non-serverless view, and then we looked at it from a computational perspective. So computer scientists joined this domain and asked themselves, so what is the computational characteristic? We are using LLMs, so we serve LLMs for prompting. We focus here on self-hosted so that we can have reproducible research. This is not necessarily what will be used in practice, but it makes it a little bit easier for us. We do see, of course, cold start effects. We heard that in the keynote. The first prompt typically takes longer. That's what we also see, what we can visibly observe. We can, of course, preload everything, but that comes at a cost. And we also see an expulsion effect. So typically, there's a time limit to loaded models. We can set that to an unlimited, but again, at the same cost. We waste memory for a model which may not be prompted for the next hour or so. So typically, we have a combination of a model, a prompt, which is, again, a combination of system context and the user prompt, a streaming attribute, and something like a keep alive metric to ensure the model does not get unloaded. And of course, we understand there's a somewhat proportional relationship between the quality, data quality output of an LLM, and the parameter size, billions of parameters, and the memory consumption. It's not a direct linear relationship, but of course, bigger models are more computationally expensive, but typically give the better results. And then we compare that quite systematically with the definitions, including quite consensus-oriented definition of what is serverless computing from 5 years ago, where we understand that it's based on utilization-based billing and unloading the operational concerns to the IT infrastructure. And of course, especially in this domain, the domain scientists, they may be experts in chemical or material analysis, but they don't want to be concerned with the IT operations. So we broke down the operation into 3 metrics: the initial load time for the model, then TTFA, time to first answer. You heard about TTFT, time to first token, in the keynote. So the first token arrives. The first token is not useful at all to the domain experts. A few more tokens arrive. The first kind of answer can be extracted from that. So TTFA is always slightly higher than TTFT. And the first answer is something like, well, this hole in the graphene layer is maybe a risk to the skin of the human. So then you need to let it answer some more because you're not sufficiently happy with the result. And only after a couple of answers, you understand that the result quality is actually bad because it skips a couple of analyses, but you only figure out later. So if you do that, and you have taken a rather small LLM to be faster, you may want to upgrade. You say it's time to upgrade to a larger LLM that will do a deeper analysis, even though it's more expensive. And this brings up the latency overall. So the quality metric we are discussing here is the so-called label consistency. So we have human labeled images, and then we check if the LLM is catching all of the issues. So the strategy looks like this. The lab experts are uploading microscopy images. We do the pre-processing, we do mapping, and then we are running a couple of strategies. The baseline is the rule-based assessment, and then differently sized LLMs. Here we have the smallest one, the tiny one, 500 million parameters, and the small one, 3 billion. And then the same 2 small ones also with the refinement, and we call them the strategies B, C, D, and E. And of course, it's a critical timing. So when do you decide to upgrade to the larger one? Because then the overall latency, you can still fix the issues you got by using the smaller model in the first place. The result, and I heard the fuck, yeah. The results, and let me just say that this is preliminary work, show that it's not really surprising. I mean, rule-based is very fast, LLMs is slow. The bigger the LLM is, then the slower it gets, but also results quality is getting better. A key issue here is the trigger. Here in this figure, we had a too aggressive, maybe 7B trigger, so we upgraded to the 7B LLM too early because we didn't have to do it. Even the 3B LLM also provided 100% consistency in the small sample we used. We also see quite a bit of deviation, especially with model B, the tiny one. This is quite pronounced, a little bit less so for the larger ones. Interestingly, is the phase analysis here. So if we take strategy D, which is the phased one, the first part is strategy C, and then we upgrade to the larger model. We see that the cold start and warm start differs quite a bit in terms of deviation, especially the warm start. And it's a little bit different in the phase 2, where the cold start difference is larger. So this means we can analyze further, especially the switching point. We saw that strategy E, which used the tiny model to start with, always led to a refinement, because obviously the smallest LLM has very poor results, whereas the strategy D, where the 3B model was the starting point, led to refinements in only 1/3 of cases, which is already better. So now we have to, in the upcoming research, focus more on the different sizes and bringing down this number. So the smaller the number of refinements are, then the more we save by starting with a very tiny model, of course. So I'm already done. It's preliminary work. It's very applied. The main conclusions I want to convey to you is LLM serving in this context a good fit for serverless. We would say yes, especially this sort of loading and unloading, which has to be done because the domain operators here cannot afford to have a full-blown LLM active all the time. We do see cold start effects, but they are maybe not the single biggest issue here. It's rather switching strategies that need to be considered. We think that this progressive loading is a promising strategy, maybe even 3 stages, which we have not yet considered in the paper. So we start with a very small LLM and go to a bigger one and go to the biggest one. What is important before we can continue our research is that we get more labeled data from the experts, because we always need that as a ground truth. In computer science, we are not experts ourselves. So thank you very much.
Thank you for your presentation. Do we have questions in the room or remote? Please remember, you can ask questions. I think Josef is in Discord channel, and we will also uploading the video recording, so you can review the presentation later on if you have some questions. Okay, so if there are no questions, go ahead. Sorry.
Can you go to the slide before the results?
So slide before the results. This one.
So why not to use LLM directly in the microscopic image instead of extracting the description using the computer vision?
So in this project, we use LLM for quite a few things. So what I concentrated on is using LLM for the results interpretation, which is one of the final steps. But the perception pipeline is what is already implemented in this web-based application you have seen before. This one, huh? So we have the whole workflow here. You see 1, 2, 3, 4, 5. And we use LLM for a number of techniques, including also the detection of flakes. So flakes are those little points you see here. We use language models also for what they have not really been designed for, which is finding image artifacts. But the results are quite mixed, so we left this out of the paper. But in this larger project, yes, we do use LLMs for a number of steps also before.
Without descriptor extraction, can we use LLM directly or?
No, because it has no data to work on. So it needs input data. In this case, it needs the metrics extracted from the image. So some key indicators that show you what kind of material is it. Does it have potential holes or folded graphene layers or dirt which got on the. So there's a lot of different metrics that the microscopy images reveal. There's a second question.
Yeah, can you go back one slide back, the metrics? So the TTFA, the time to first answer, is there, like you said, like we're not looking at the first token because the domain expert need to have some amount of proper answer for this. Do we have a definition that it has this X amount of token, or is it proper different choice there, or it's just?
Yes. So just to repeat the question. So the question is how do we determine after how many tokens do we have an answer? So if we get the text answer, so we have to typically wait until the sentence, the statement is completed. But if we get a structured answer, even in streaming, we get something like a data structure. We need to wait until we can parse it, because the data structure is built up incrementally. And after each token that we receive, a parsing attempt is being done. And when it's successful, then we can try to see what's in it, and we can compare with the baseline metrics. So if you ask an LLM to interpret this image for the image metrics, it will write something like, I think based on this metric, it's dangerous for human skin. And if you don't wait until the word skin, you get a partial result, but you don't know what the danger applies to. So you have to wait until a certain number of tokens have arrived.
The reason I asked the people, because the formal number, like 50 tokens, that matrix will keep on changing, right?
It will keep on changing because it's heuristic. So sometimes the LLM, of course, also writes a number of things before it gets to the interesting results, which is due to the nature of how they are constructed.
And one more question to just follow up on that. So coming back to the cold start, you said you observed cold start in this. Now you're using LLM to generate an analysis report. Is cold start a worry there? Like cold start is a more thing where it is a latency sensitive, application where the next function depends on it.
We do, yeah. So the question is about the latency, the sensitivity of the report generation. So this is an interactive application, and in the end, if you go to structure a summary, the expert wants to generate the summary and read it before maybe handing it off to the government. So the expert's time here is also a matter. The expert doesn't want to see, please come back in 1 hour, we will generate the report, but wants to read the report after just a few seconds time. So if the generation time is taking too long, the expert will unlikely adopt such a workflow.
So cold start is more into the report total and report generation.
Yes, part of the report generation.
Thank you.
Okay, thank you.
Thank you. Great talk, great questions. And Austin, can you start your talk? Okay, I can see your screen. You have 10 minutes. I will beep 9 minutes mark. Go ahead. Everything looks good.
Hi, my name is Austin Bomhold from the University of Washington.
Actually, your audio is not very good.
Heard it all? Hear me?
Try again. Hard to hear, and it's like there is some extra like metallic sound. Maybe get closer to microphone.
Yeah, this is
now much better. Yeah.
Okay, I'll just have to do it like this. Sorry. Hi, my name is Austin Bomhold. I'm from the University of Washington, and I'll be giving my speech today on InferenceProfiler. We're going to look at the performance, cost, and energy of LLM. So first things first, let's look at our motivation. Observability in the cloud is important. It's needed for optimizing both cost and energy. For get visibility into the host of GPUs and inference engines, but each one of these layers has its own independent tooling provided by each one of the layer vendors, which will sample the resources and track timestamps independently from each other. And the tools change based on hardware and environments. The goal here is to single time-aligned view of the different performance counters across various layers. Background, just quick reference. LLM's auto-regressive, so the main limiting factor with these is going to be that each output token needs to be processed with the next output token, creating a linear relationship. There's also 2 phases per request. We have a prefill, which processes the whole prompt and emits the first token, and our decode phase, which is some. Additionally, you have a KB cache, which stores massive values. Each step rewards recomputation, and it grows sequentially with the length. Second, in different inference engines, the software tools that can manage request scheduling, KB cache allocation, and continuous batching or.
Alex, the quality of audio is extremely bad, I think.
Yeah, so Austin, do you have any other option for your audio?
I do, but it'll take me a second. I'll have to rejoin. So I don't.
Yeah, go ahead. Try it. I mean, I can understand it, but it's really like 8-bit analog.
Okay, would you rather me just get closer and talk louder, or would you rather me go get the headphones?
It's both louder and now I can hear you, but Pedro, how you hear it?
Yeah,
go ahead.
It's improved.
Okay, so I'll just talk louder. Sorry. So it's a crowded space. You have a bunch of different inference engines. There was a recent paper out of from ACM out of Korea, looked at about 30 different inference engines. We eventually landed on VLM, mainly because of its graceful degradation. It was never the fastest or the highest throughput necessarily, but it managed the highest concurrency without crashing, basically. Second, basic LLM performance metrics. You've heard these mentioned before, but this is just a quick recap so that when I mention it, talking about inference performance. So first, time to first token, TTFT. Time from the request to reception of the first token. ITL, or inter-token latency, is the time from the previous token to the current token, so in between each next. And end-to-end is simply the sum of TTFT plus each ITL. It represents the full round trip request. Finally, we have tokens per second, throughput of output tokens. It's simply just each token divided by the duration. Now that we understand the background, methodology for our experiments, the actual tool we use to collect is a homebrew Go profiler. Runs next to the actual engine, collects it as a sidecar, and then it aggregates across 5 different metrics groups: VM and C group, process, GPU, and VLM. To produce that single time-aligned record that we mentioned at the beginning. Records are nanosecond timestamps per metric, and each collector runs in its own Go routine and uses an internal cache. The cache allows it to avoid time skew, and it allows it to propagate the timestamp up from the source. Second, in order to make any observations, we first need to measure the actual overhead of how we're collecting this. So we looked at it versus not profiling it. We used Meta's Llama 3.2 on a GD4D and X large with a T4 GPU on AWS. Did a 50 max concurrency with 500 requests, and then a simple fixed prompt input and fixed prompt output of 512 tokens across all intervals. The profiling intervals, our mean end-to-end latency stays within 0.14%. So then what instances did we actually look at? 4 generations, roughly 6.5 hourly on-demand price range. And our goal is to figure out which one is the best inferencing throughput per dollar. For our server, we use VLLM with chunk prefill and continuous batching, same model as before. The client was the VLLM benchmark client on a T4G. Separate instances in the same main Z, random prompts with fixed tokens. We trusted 2 workloads, 1,000 requests, 50 max currency with 512 input, 512 output across all tokens. And then a workload 2 was 100 requests, 1 current request, and then we vary the input and output. Simply, the first results of workload 1, cheapest cost per output is the G5X large, the A10 at 0.183 cents per million tokens. That's output tokens. The fastest was the G7E, the RTX Pro 6000, and doubling the vCPUs on T4, just plus 2% to throughput, but plus 40% cost. The NTNT, the end-to-end latency separates cleanly by type, except for the G4DN instances, which share the same GPU. The G4DN shows the largest spread, largest tails, TFT in 3 bands. You see the grouping between 100 and 500 milliseconds, latest 2 generations, 500 to 1,000 milliseconds, the last 2 view, and then 1 to 2 seconds for the G4DN. The long tail, traverse token tail on every instance is the most pronounced on the slowest of the instances. T4. Second, or finally, we look at the energy costs, the energy efficiency of each one of these instances. G5 being lowest, the G7E being lowest energy, and the G6E sits between the G5 and the G7 on both cost and power. The G4DN and the G6 are dominated in both parts by at least 1. And then finally, our InferenceProfiler unifies as host, GPU, and engine telemetry into a 1 time-aligned record, less than 0.14% overhead, and instant latency. Most cost-effective instance is neither the cheapest per hour nor the fastest. G5 coming in at $183 per token for million tokens. Cost and energy are distinct targets, no instance wins both. And concurrency is the dominant lever for cost efficiency. The 50 concurrent request was roughly 26 times cheaper than sequential on the same G6.